Welcome along, everyone, and it's great to see so many people here. I know a lot of you, but my name's Mick, and I'm the project officer for the Chemistry Education Association. This year in the November lectures, we've got today's lecture, and then next Wednesday, we'll have some workshops. We've got a slightly slimmed down November lecture program this year, but Seamus, who is over there on my screen, he'll be doing one of the workshops next week, and Emily Rochette, who I can't see on my screen right now, she'll be running the other workshop. I am going to start though by acknowledging that I'm on Wurundjeri country, and I want to pay my respects to the traditional owners of this country, the Wurundjeri people. I particularly want to pay my respects to their long tradition of teaching and learning, and I hope that at least some of the things that we do today that are respectful of that tradition, and follow along with some of those very long-standing processes. But now I'm going to pass on to Seamus. Seamus is going to briefly do something that is not a plug, a recommendation, but I'll pass over to Seamus, and he'll talk about something that he's going to be doing this year, and then introduce Doug. So off you go, Seamus.
Thanks, Mick. Yeah, before I have the honour of introducing Doug MacFarlane, just quickly tell people about we're just opening it now for expressions of interest to be involved in the CEA Professional Learning Communities Program. It's run fairly successfully for the last 2 years, albeit with COVID and albeit online. In next year, we're running it yet again. If you haven't heard me talk about it before, it's a free program, a free professional learning program that's financially supported by the CEA. We look to try and get about 15 to 20 teachers involved every year. It involves 2 days of professional learning towards the start of the year, where we sort of set you up, and it's a year-long journey where those first 2 days we show you a lot of great, inspiring, contemporary education research in chemistry, and then we design activities to do with your students, and then collect those results. And the payoff at the end of the year is that you feel like you have something to show to the chemistry education community. So in the last couple of years, our groups have presented at STAV. We're supporting the 2020 groups at the moment to write a couple of papers that go into teacher magazines and so on. So it's really about paying it forward and you becoming part of the education community, as well as improving your teaching practice. So yes, that's the link there. I won't say more than that. We've got, you work with groups of 3 or 4 teachers, and it's also a way for you to get to know some other chemistry teachers across Victoria. So we really encourage you to work with different groups, and we mentor you all along the way. So that link is there. I'll put the link in the chat as well. And of course, any questions at all, do let me know either through the link or through email. Okay, so stop plugging. Now, I'm going to quickly introduce Doug MacFarlane, who is the Sir John Monash Distinguished Professor in the School of Chemistry, Monash University. I think you were also my head of school at one point, Doug. Doug is also leader of the energy program in the ARC Centre of Excellence for Electromaterials Science. He is currently researching materials that will enable new pathways to generate energy and fuel from sustainable sources. One of his main focus areas within the ACES is the generation of green hydrogen and green ammonia from nothing more than air, water, and sunlight. He has published more than 800 papers and 30 patents. His awards include the Australian Academy of Science Craig Medal and the Victorian Prize for Science and Innovation. He is also the founder and Chief Scientific Officer of Jupiter Ionics Proprietary Limited, a company spun out recently with seed funding from local investors to scale up the green ammonia generation technology developed in his group. Wow, it's such an honor. Thank you, Doug MacFarlane, for your time today, and the floor is yours.
Okay, thank you, Seamus. And let me just start sharing my screen. Okay, here we go. I think hopefully that is visible to everybody, mostly. Okay, great. Honored to be able to talk with all of you this afternoon. It's always a great pleasure to pass on some of the research that we're doing in our area to you all as the engine rooms, if you like, of technical education in this country. It was an inspiring chemistry teacher at the end of high school that certainly set me on my ways towards a career in chemistry, with a father that wanted me to do engineering and other forces that wanted me to do medicine, but it was a chemistry teacher that sorted me out. So good to talk to you. There's a number of references I've got here, and in particular, I think this one called on the right-hand side, called a roadmap to the ammonia economy. And this ammonia topic, which is part of what I'm going to talk about today, is hopefully a good read for you all, and even for some curious students, some students that are curious about all of this. I think they would be very accessible, so I can happily provide copies of that one way or another to anybody who's interested, although I think it's sort of freely available if you search that title online. So I'm going to talk about, that's interesting. Yeah, I'm going to talk about just why there is this buzz in Australia around renewable energy picture, and in particular about hydrogen, first of all, as an energy carrier, and then to start to talk about where ammonia surprisingly fits into this. And there's a reason hydrogen as a concept, as an energy carrier, has been around for a long time, but ammonia is a much more recent sort of concept to appear on the scene. About that point in this talk, we plan to have a bit of a breakout discussion, separate you all into some smaller groups, give you a chance to discuss a topic which is directly relevant to the appropriate VCE unit. The sort of the topic there, we'll draw out some of the concepts, and then we'll come back and share some thoughts about that, and then we'll finish off talking about some of the cutting edge science that's coming out of our group in recent times, and then finish off with hopefully leaving plenty of time for questions, as this is a topic that usually does create lots of discussion, lots of great discussion. So just quickly on this important role that Australia plays in this renewable energy topic, here's one of my favorite slides, which shows you the total solar insolation, that word meaning the amount of solar energy reaching the surface. And in this case, it's averaged over the whole year, and night and day, and then plotted globally. And what you see is it ranges on, if you look at the scale on the bottom carefully, you'll see that the dark brown colors are nearly 300 watts per square meter continuous. So that's, because it's averaged, it's a number that represents the energy that overall is on average raining down on that square meter of territory. And so the brown colors are nearly 300, and then if you look at the blue and purple colors, they're less than 100. And then if you look at the parts of the world where those different colors crop up, clearly there's really nowhere quite like it on the planet, quite like Australia, meaning the center and the northwest. And it always amuses me, as coming from that part of the world originally, that clearly Northern Europe and the UK and Ireland are, it's sort of forget it in terms of solar energy compared to Australia. And what that means is that the same solar cell placed on these different parts of the world, and the ones that are going to be in Australia could be 3 times more productive, same solar cell, than they would be, for example, in Germany or in the UK, 3 times more productive. And that little yellow square then sort of puts this into more concrete sort of perspective. If you put ordinary commercial solar cells onto that little square of land, which is 250 by 250 kilometers, you can generate 25 petawatt hours per year of energy on that. And with my undergraduate students, I'll sort of let them have some homework and go and figure out what that represents. It's an amount of energy in terms of electrical supply, but is it what? Is it Australia's electrical supply? Well, to cut to the chase, it's the whole world's electrical supply from that little yellow square. And of course, most of that land is relatively of relatively low productivity and low in habitation otherwise. In fact, to put it in perspective, it's about the same land area, combined land area of Australia's 4 biggest cattle stations. So we're already using that kind of area in a relatively sort of low productivity way. And most of those cattle stations would be only too happy to have an alternate source of income. So the question is, how do we get that energy out of the part of the country and to our own cities and to the massive centers of population to the north? Or in other words, what's in that boat is the question that we're going to talk about a little bit here. We refer to this concept of solar and wind energy. I could tell the same story about wind energy, and there's plenty of wind energy in Australia as well. We refer to this, though, as liquid sunshine. It's a lovely concept, taking sunshine and turning it into something liquid that we can easily transport. The gaseous forms of any of these compounds are far too hard to transport efficiently. So the first, and before I go on with talking about liquid hydrogen, that lovely term, liquid sunshine, was the title of the paper that you see in the bottom of the slide there. But you notice it's not quite the title that we used in the end. The original paper was called Liquid Sunshine. And just as we got to proof stage of that paper, one of my people came in and said to me, looking at me rather curiously, said to me, "So Doug, where did you get that liquid sunshine phrase from?" I have to think back. I thought it was probably from some journalist or other somewhere, some point or other. And she said, "Before we publish this, you should look that up in online, see what you find." So I did, and within a couple of Google lines of my Google search, I came across the Urban Slang Dictionary, and it turns out the liquid sunshine is a well-known slang for LSD. So I thought, this probably isn't a good phrase for us to be using. You could just see the headlines that might emerge from that. You know, Monash professor planning a major export of LSD based on renewables. Anyway, moving on, hydrogen. So hydrogen is of course relatively easy to produce by electrolysis. And this little movie that you see playing out here is showing us electrolyzing some salty water. And I've added a few details there because it's actually a very easy experiment to set up. If this isn't already part of something that you do with the students, then I suggest you could have a look at this. It's a simple 9-volt battery, some standard copper wire, electrical wire. The solution can be some simple salt, preferably not sodium chloride, because you end up producing some chlorine at the anode, which can make it a bit smelly. And otherwise, you know, even the stoichiometric 2-to-1 ratio is even apparent in these test tubes as it unfolds. So, but the only thing I would say in recommending it as a good experiment is to think a little bit about if you have the students doing it themselves, think a little bit about the safety of the hydrogen, and preferably don't mix the oxygen and the hydrogen because it gets even more explosive. So safety is an issue with doing this in large volume. So hydrogen is easy to make, and I'm going to talk a little bit more about that. And here is some deeper detail of what goes on. There are the traditional, sort of relatively well-known electrolysis cell that is sort of in common use around the world for making small amounts of hydrogen, involves this water splitting reaction. Two reactions, one on the anode, one on the cathode, both starting with water. And in the case of the alkaline condition, which uses concentrated potassium hydroxide as the electrolyte, the electrodes are typically nickel. just simple nickel, and on the anode side, the nickel oxidizes readily to nickel oxide, or one of the nickel oxides, to do the reaction. But in the end, those nickel electrodes are really not very catalytic towards the process, and the net result is that whereas we should only need about 1.23 volts for the overall thermodynamic potential for the reaction, a bit more than that would be ideal. In fact, the typical cell voltage is more than 2 volts in that case. Where this is heading more recently is to recognize that the water reduction reaction is much more facile with acidic water. In other words, its protons are reducing when it's an acid condition, so sulfuric acid now. And this is also called the proton electron electrolyte membrane, or PEM electrolyzer. So then the cathode can be relatively small amounts of platinum, although there's a lot of work. I should say the cathode catalyst is small amounts of platinum, usually on a carbon type support, and a little bit like a fuel cell, same sort of electrode. But the problem that comes up then is the anode reaction. There aren't very many materials as metals or metal oxides that will be stable in acid at high positive potentials. So you end up basically dissolving them off if you're not careful. That would certainly be true of nickel. So in the end, the famous the active one in this case is iridium oxide, which is a terribly expensive material and terribly scarce. So that's not a good choice when it comes to sustainability. So this is a bit of a conundrum. We need to develop better catalysts for this overall process under the acid conditions. And to cut to the cutting edge, so to speak, here's an example of such a catalyst from our group a couple of years ago. And so remember, the challenge here is a stable material that does the water oxidation reaction, the oxygen producing reaction under acid conditions. And in order to stabilize these, we took lead oxide, which famously from the lead battery story, of course, is well known to be very stable under acid conditions, and doped it with effectively, or co-mixed it with cobalt and iron oxide. So it ended up as a 3-metal mixture in the oxide lattice. And you can see in this picture, the material is extremely uniform even at the micron level. So this is probably a solid solution of the 3 oxides. And the lead oxide tends to stabilize it. And the data you see then plotted there, the dotted line is our thermodynamic equilibrium, 1.23 volts, where everything should start. Under alkaline conditions, you can see there's much higher voltage that's required to drive the electrode into water oxidation. But under acid conditions, that gap between equilibrium and 1.6 volts is a very respectable amount of extra energy, or overpotential, we call that, to drive that reaction. So that is a good catalyst, basically. An important point about this in terms of sustainability is that because we deposit this catalyst from the original solution, the electrolyte in the first place, by adding small amounts of cobalt and iron and lead into the solution, lead ions, and therefore the active catalyst materials are always present in this solution that is the electrolyte, and therefore if the catalyst tends to degrade because of bubble formation, tends to be quite a rough experience at the nano level, and also just thermal cracking of the material. The cracks can be healed or self-healed, and the catalyst then overall has a much longer lifetime, because the lifetime of these catalysts, especially these precious metals catalysts, is a bit of an issue. I'm going to talk a bit more about that in our breakout session. So the problem with hydrogen is, so we certainly can do water electrolysis. The problem with hydrogen is that in large scale, the scale of bulk oil tankers is a technology we just don't have at the moment. We've never had to develop that globally. And of course, there's some ancient history here in the Hindenburg disaster that reminds us that large amounts of hydrogen gas are terribly dangerous. And the problem with liquefying it, back to our liquid sunshine, liquefying it consumes about 1/3 of its energy to get it cold enough to -253. in order to get it into its liquid state, and then into some, as yet more or less, the technology of those ships is still developing. Now, some of you might, who are on top of the thermodynamics here, may say something about consuming to never get it back. About a third of its energy doesn't quite make thermodynamic sense. So let me explain that a bit more. So basically, what this would say is, if you had 100 tons of hydrogen as a gas, you'll need to use about 30 odd tons, 33 odd tons of that in a fuel cell to drive the refrigeration equipment that is otherwise liquefying the other 66 tons of hydrogen. And that amount of hydrogen is then completely lost. The energy content of that is lost in the process and never arrives at destination. So it's expensive to cool, in other words, is the outcome. So can we do something else better than that, better than liquefied green hydrogen? So we call this the Gen 2 concept. And now we're in the concepts of literally the last 5 years is when all this has bubbled up. We can make ammonia using the Haber-Bosch process. So ammonia has been made for about 100 years by a famous catalytic reaction at elevated temperatures and pressures all over the world by this process we call the Haber-Bosch process. But as an energy carrier, it's actually quite good. We can liquefy ammonia at room temperature by only increasing the pressure to about 12 bar. That is very normal. And as a liquid fuel, so to speak, it carries about 22 megajoules per kilogram. That's about half of hydrocarbons, of petrol and diesel, half. So, you know, our petrol tanks, etc., will have to be bigger, but not very much bigger. And really, you should think about this as being a little bit like LPG. So wherever we can use LPG, we can use ammonia. And there was a picture of this in one of my previous slides, but this is one of our Haber-Bosch ammonia plants in Australia. This one is up in Karratha in Pilbara, far northwest. And these are already existing in Australia, and they ship ammonia out of this plant all the time. Today, it works on fossil fuel hydrogen. You might ask, why is it way up there in Karratha? The answer is there's lots of natural gas. So the hydrogen comes from the steam methane reforming reaction from natural gas. So that's why they are where they are. But the green hydrogen-based process can be anywhere there's lots of green hydrogen. So ammonia has got a lot of future in this. How does this work? Sort of, if you're going to make ammonia, so what are you going to do with it? So here's sort of a sketch to show you how this works. So we can make green hydrogen. We can turn it into ammonia. That's the standard Haber-Bosch process, and put it into standard ships. Take it to market, and this could be in Tokyo. Is very much into this, and use, one option is to use a cracking technology that CSIRO has developed that basically converts the ammonia back to nitrogen and hydrogen. It's a relatively simple cracking of the ammonia. Then we have our hydrogen. We can put our hydrogen into fuel cell vehicles and other uses of the energy. This is the Toyota Mirai, and that's me actually sitting in the I was actually driving it prior to this photograph. And I'll have to say that it was a very nice drive. I would love to have one of those cars. It's effectively an electric vehicle, but running on a fuel cell source with hydrogen tanks in the back. However, that's just one option. If we reflect on the fact that ammonia has actually been used in ordinary combustion engines for a long time. So this is a picture from Belgium in the Second World War, and the tanks on the roof there are the ammonia tanks. Ammonia burns a little bit like diesel once it's in an engine, or you could think of it again a bit as LPG. And in more modern times, Mitsubishi is developing electric power turbines running on ammonia, just like they run on natural gas. Shipping is almost certainly going to start to use ammonia to replace diesel. By around about 2040 to 2050, they think that it will almost entirely be ammonia. There isn't really much else, and hydrogen is not the answer. And even jet engines, believe it or not, I find this one hard to believe, but actually by the time you heat ammonia up in the pre stages of the engine, it's already decomposed into hydrogen. So it's like running it on a hydrogen source. And finally, ammonia can be introduced into a traditional coal-fired power station, and you get the energy content of the ammonia. So you can co-fire with ammonia, which is a good way to transition from coal to ammonia, pure ammonia power generation. But this needs to be said always, if we have green ammonia, don't we need to green up farming first? I mean, most of the ammonia we produce today goes into fertilizers, almost entirely. Only a little bit for the chemical industry. And the answer to that question then is very much yes, because there is an important issue here, which is very much about the climate. I call this a sustainability nexus, because on one hand, the Haber-Bosch ammonia process produces most of the, supports most of the agricultural on the planet, without which this planet could not support a fraction of the population that we currently have. On the other hand, it alone, the process alone, produces about 2% of global CO2 emissions. And that's not the end of the emission issue with ammonia-based fertilizers. So there's a real problem here. So we have to apply green ammonia here first. And for cost reasons, that's basically what will happen. There are real advantages to a farmer. Here's an example of an ammonia tank being used with direct injection of ammonia into the ground. This is a well-known process in certain crop growing, like cotton and wheat in certain parts of the world. And one of the reasons for doing this is it also helps to reduce loss of ammonia, loss of N, whatever form it's in, from the soil. So a lot of the fertilizers that are applied as a reduced N form never are absorbed by the plant because of the way that it's applied. So having more distributed forms of fertilizer generation, such as being able to make the ammonia locally, as we could do, I'll explain that later in this talk, may help us solve some of the other emissions to do with farming. And decarbonizing farming is a big issue. So how are we going for time, right? This is a good point to break then. So recognizing one of the key dot points in the VCE and the unit outline, the point here is that the electrolysis cells, whether it's hydrogen, and I'm going to show you ammonia later on today, they are like, because they can be made small, if we assume that the whole process can be, whether it's hydrogen or ammonia, can be made quite small, they're going to be installed, certainly, on a widespread distributed basis, meaning in communities, on farms, and in industry. So the question then is, how could the development of electrolyzer design deal with the green chemistry lifetime issues once it's sort of out of control of the large-scale chemical engineering industry? The issues of performance degradation, in other words, just not working as well as they should, materials recycling, they certainly have a fixed lifetime, so they do not operate forever. And remember, there are some scarce materials, even our favorite catalyst that I talked about before has cobalt in it. That's a contentious material in the world right today, and of course minimization of other harmful wastes. So how do we deal with those issues as we begin to design these electrolyzers for widespread use? So with that in mind, Mick or Seamus, do you want to tell us how this is going to work?
Yep. So you've all got a job to do, and that job is the thing on the screen right now. I'm going to put you into breakout rooms, and you'll be in those rooms with 3 or 4 other people, and I would like you to pick one of those 3 topics, either talking about performance degradation, materials recycling, or minimisation of harmful waste. And I'd like you to put your comments onto the Padlet. So I've just put a link into the chat. If you click on that link, a Padlet screen will open up. And on that Padlet screen, you'll see those topics. And all you have to do is talk to each other and then write down some things that you think might work, or things that you might have more questions about. And then we'll come back and we'll be able to see what you've been talking about if you make sure you remember to write those things down. And then Doug will be able to talk about them during the second half of the session. So I'm going to put you into those rooms now. Click on the link and I'll make sure, in fact, step one, click on the link so you've got the window open. So that link is in the chat, and it's that really conveniently labeled link, that one there. Make sure that's open. Within your breakout room, make sure someone is taking some notes. Pick one or more of those topics to talk about, and then we can come back in about.
I don't know how to get into the breakout room.
That's because I haven't told you how to do it yet. To get into the breakout room, and Gay, I'm so glad that you asked. All you have to do now, so I'm going to click on a button that says open all rooms, and you now have an invitation on your screen that says join the breakout room, and so you just click on that invitation, and I can see that many of you are disappearing, so that means that it's working, and have a chat about these couple of ideas, and then we'll come back in a few minutes and talk about them. All right. Thanks, everyone. I can see that you've had a few really interesting discussions on the Padlet, and that's going to stay open. So if you have other things that you're thinking about now that you would like to ask, it's a really, I mean, Doug's been looking at that, so it's a really good way to get your questions down, and you can kind of see if everyone's asking the same kind of questions. So welcome back, everyone, and back to you, Doug.
Good. Lots of good comments here. I'm just absorbing them all at the moment. I think grouping a number of comments together, I think, you know, the cobalt that I pointed out is a good kind of jumping off point for this discussion, because it is such a hot topic in the world today for two reasons, of course. One is that it is effectively almost a conflict material, as in it comes from parts of the world where sort of the origins of it are often sort of embroiled in conflicts and poor practices and slavery and poor safety and so on and so forth. But secondly, also that it's actually quite a scarce resource, and that there isn't probably enough known resources in the world even to supply the projected lithium battery needs for it, never mind electrolyzer needs for it. So the simple answer to that one is it's a sufficiently troublesome metal that already, sort of driven by that understanding, we are looking for substitutes for it that are more benign in every sense of that word. And you know, somebody else was asking about, you know, what is it that you try to you think of recycling here, and recycling out of material out of devices like this is a relatively new concept. I mean, the industry to recycle batteries, especially lithium batteries, hardly exists at the moment, but it needs to, and it's emerging. And the electrolyzer recycling industry also needs to kind of gear up eventually, but I think will be much guided by and led by the nascent lithium battery recycling business. It's a similar kind of device in many ways. So there's lots to learn as that emerges. But in terms of what do you recycle, the answer is hopefully more or less everything. There are almost no metals. I'll just get you to think of this for a moment. There are almost no metals that aren't sufficiently scarce and therefore expensive that it isn't worth considering how to recycle them. So like the only two that I could think of that you might decide are sufficiently common and are easy to dispose of in a completely benign way would be, you get your students to think about this, probably iron and aluminium. just about everything else is too valuable to not recycle. But then there's also the carbon, the electrolyte components. There'll be some salt in this, potassium, for example, in the alkaline cell, and this is a tremendous problem in the lithium battery industry, recycling at the moment, because in the end, you have to try to physically separate some of these bits and pieces before you can try to do some chemical separations. This becomes a big, so the science of separations, chemical separations is a growing science because of this. But the approach which is current, believe it or not, of just taking the whole thing and grinding it up is actually a very bad idea, because it's actually making the separation worse, not better. But it is what people are doing at the moment, and it's just a sort of surprising step. So designing for refurbishment and so disassembly and reassembly, I think is a key concept in almost everything today. But certainly these electrolyzers should be designed and built in such a way that they can be easily refurbished with some part of the degraded electrode. It's probably just the electrodes, like taking the electrodes out of a lithium battery and just putting some new ones in, taking the old ones out to reprocess. And there is good example here, believe it or not, of the electrochemical industry doing this, despite some of the things that you've heard about, of course, even locally here in Melbourne, about lead in soil and whatnot, which comes principally from a lead acid battery manufacturer, not only, but mostly from over the years. In recent years, meaning the last 30 to 40 years, the lead battery industry has managed to achieve something like 99.9 something, right? Use and recapture and recycling of its lead. Right, so there's good examples of that industry, kind of for both environmental reasons and for cost reasons, of really getting it all under control. And of course, it also includes, in this instance, includes us as consumers, and we don't just we shouldn't throw lead batteries away into the waste. So this can be done, and things like this can be disassembled and the materials separated from one another and then chemically further separated as needed. So I think that probably answers many of the things that were raised there and sort of gets the discussion going. I might just take a couple of minutes, or 5 or 8 minutes, hopefully, here to sort of finish off with talking a bit more about ammonia. So let me just go back to my slides, and here we go. And then we'll come back for more questions. So let me just keep going here. So yes, as you might have expected, ammonia is Gen 3, but we're not going to use the Haber-Bosch anymore, because the Haber-Bosch actually is a hard process to scale down, and it itself is expensive and uses catalysts and so on. So avoiding it and making ammonia by electrolysis directly is what Gen 3 is all about. So the cell, the electrolysis cell, is very much like the hydrogen electrolysis cell that we looked at before. So I won't say any more about that, other than that we're taking in nitrogen from the air. So this is effectively air being separated into its nitrogen component, reacts on the electrode, and rather than this being an electrode that produces hydrogen from water, it produces ammonia from nitrogen and water. So that's the concept. It is hard, though. So if you look at the electrochemical series, it is easier. Let me start off again and say it's easier than you might think, even though it's not really ever been done before, because the electrochemical series shows it to be easier to reduce, according to the E0 value, 0.3 volts compared to producing hydrogen from water, which happens at 0 volts. So you might look at that and think, a high school student would look at that and think, hell, that should be possible. Actually, there's a problem in that if we can't get this happening before hydrogen evolution begins in an aqueous solution, then because it's the solvent and nitrogen is not very soluble, especially in water, right? Then water reduction takes over and we just get a lot of hydrogen and a tiny bit of ammonia. So that's the challenge, right? One of the answers to that challenge is to not do it in water. And there's a process that's been known for quite some time, and then we sort of improved it in a recent paper in Science, which is this structure here, and the solvent that is the white stuff in my slide here in between is almost exactly the same as a lithium battery. And we're operating at lithium potentials where on a copper cathode, that's what's in a lithium battery, nitrogen, if it's present, it isn't present in a battery, but we purposely put it in here. We formed this compound called lithium nitride, a relatively well-known reaction. Every lithium battery manufacturing plant knows very much about this reaction to produce this stuff. But also, if it gets anywhere near a source of protons, and I've written this just here for the moment as a BH, this is an acid with some conjugate base B minus, these protons will quickly form ammonia and give you back the lithium ions. And if the hydrogen ions are being produced from hydrogen or water at the anode by the corresponding oxidation reaction, this becomes a cyclic process. If B is doing its job and not doing anything else, most of the rest of what's on that slide except B are relatively well known. So what we did very recently was we picked up on a moderately obscure bit of organic chemistry. I learned about this in undergraduate and then promptly forgot about it for 30 years. But came back when I was looking for something that might suit this cycle that's needed in this cycle. And these are phosphonium, or phosphorus-based cations. They're actually made and used for a lot of surfactants. But it's well known also in a process called ylide or eyelid formation, so people say that different ways, that this proton on the carbon next to the phosphorus is relatively acidic. So it will be the source of this H here in my ammonia. And as long as it cycles around and gets reprotonated, it becomes a shuttle for the protonation reaction, then it will do its job. And that's what we showed in this paper that was published in Science earlier this year. I might, in the interest of time, skip over how we know that it's doing that, but some phosphorus NMR was really useful in that regard. And I probably don't have time to do this either, but there's a YouTube video that we had all of the guys in the lab talking about what they do. So it's reasonably entertaining for a science video. If you wanted to recommend this to any, this is on YouTube, so you could recommend this to your students if you wish. But I'll skip that, I think. So let me just go on and just say that today we've got materials now that produce on the right-hand side, in the blue points, we're now producing nearly 100% efficient reaction to ammonia. Very important that this is a sustainable process to be reacting in some other way that is consuming something else in the cell. So that's really important, and that the yield rate, we use obscure units here, but if you convert that into everyday units, this cell is producing a couple of kilos of ammonia per day on a square meter of electrode, and that's a practical result, shall we say. So that's the topic, if you like, of the technology that has been picked up by this spin-out company called Jupiter Ionics that we've formed, and that device in the foreground there, which is about the size of an iPhone. It'll eventually be a bit thicker with stacked cells, but at the moment it's got a couple of cells in there. It's the sort of one that could be used on a farm to continuously producing ammonia for a commercial greenhouse, or anywhere where there's a continuous irrigation type flow of fertilizer being used. That's called fertigation, and that's quite common on many horticultural applications like growing grapes. Just before I finish, this is a slide that one could talk about for a long time, but we've always been very aware of the impact, if you like, of further use of ammonia than it even is used today in fertilizers. A wider use of ammonia could potentially have a wide impact on the global nitrogen cycle, just as our use of hydrocarbons and coal have had a very big impact, badly, on the global carbon cycle. So we don't want to repeat that mistake, obviously. And this is, in all of its glory, the global nitrogen cycle. And I'll just sum up sort of what we know about this, which is not everything. There's a lot unknown about this, and we just published this in order to make the point that a lot more needs to be studied. There's a lot of good ocean science, ocean chemistry, atmospheric chemistry that needs to be understood before we continue to make mistakes with this. I'll just skip through all of this. So there, in the end, then, is a summary of how this hydrogen ammonia concept could work. One of the key platforms then being the production of ammonia from our renewable energy. So this is the electrolysis cell. The product, which is very storable and pipelinable, being ammonia, which ultimately, in some contexts, for example, for vehicles, could be regenerated into hydrogen. But in other, especially heavy transport applications down the bottom here, could be used directly in sort of effectively replacing diesel wherever diesel is used. But most importantly, from the very beginning, most importantly, I think the first use of this kind of green ammonia will be in greening up farming, which at the moment actually is an uncomfortable truth, which is that our food is a fossil fuel product, and we're going to have to fix that problem before we can fix many of these other problems. So with that said, I will just thank everybody and open it up for questions. So either a continuation of our previous discussion or any other questions that you might want to ask.
Well, thanks very much, Doug. And does anyone have any questions?
I had a quick, inexperienced question. I was just wondering about the cracking of the ammonia that you were talking about. You were saying it's a fairly simple process, and in all your diagrams, you've got ammonia coming in and then hydrogen coming out of the tank. Is that something that could happen at the site of distribution? Is it that simple?
Absolutely, Melissa. That's exactly how this could work out. So it could literally be, imagine the center of Tokyo, the thing that is delivering the energy, so to speak, is actually a tanker full of ammonia. You might, at that point, you might sort of squirm a bit and think, really, do we want that? But come back to that question. And then in the, underground next to the tank in the petrol station, which is now a hydrogen station, is where this is happening. This cracker technology is a relatively simple device, and then what's fed into the car is the hydrogen. Or even going further, it could be on board in the car.
Oh, right, yeah.
Yes.
So a follow-up question was, if you didn't do that and you in like the heavy vehicles and you've got ammonia that you're combusting, I presume. So I didn't really know much about that reaction, but I've just looked up that it makes nitrogen monoxide. So I'm assuming that has polluting issues in itself. Is it do we get onto acid rain issues, and is it a greenhouse gas?
Yeah, no, this is a very important question, and it's sort of part of the reason for that last slide, which I had to skip over it. So it's almost a seminar in its own right, or a study for a bright, VCE student. The intended product of any use of ammonia would be dinitrogen back into the atmosphere, effectively where it came from, and huge amount of it around us already. So it seems like it's a sustainable cycle if it's mostly nitrogen. However, as you've said, the oxides of nitrogen, all of them, there's lots of them. It's a very, very complex, area of chemistry, nitrogen oxides, are readily produced, especially in combustion, right? However, fortunately, there is a very well-established technology for dealing with NOx emissions, right? It's because NOx emissions are already part of every engine today. And if most people didn't know this, includes me, I didn't know this until somebody pointed this out to me a year or two ago. This is already true that a lot of trucks and even all the way down to small delivery type van cars, vehicles will fill up, not only fill up with diesel, but will fill up with something called AdBlue. Look for it next time you're in the petrol station, or ask where it is. But it's a separate little tank. It's a bit like the tank full of your windscreen wiper wash or something like that, but it's usually accessible outside the vehicle somewhere. And what it is it's an ammonia solution, or a urea solution, effectively ammonia, right? Because urea plus NOx, any of the NOx compounds, there's lots of them, right, will give you dinitrogen. So the NOxes are oxidizing agents, the ammonia is a reducing agent. So you put the two together and you get dinitrogen. So the engine management system injects a small amount of this ammonia solution in these engines under fairly sophisticated control to basically knock out the NOx emissions fairly well. And the net result is that when we look around Melbourne and see our slightly yellow atmosphere, which is one of the NOx compounds, it's mostly from our own domestic vehicles. It's not from the trucks and the bigger heavy vehicles, because they're all NOx controlled by what I've just said. So look for that in the petrol station next time. AdBlue. It'll either be somewhere around where you're filling up, or it'll be on the shelf inside. Existing technology, and works very well. So that's an important kind of, what should we say, stepping stone to making this practical in a non-polluting way. Otherwise, this would be frightening. Everything I've said would have been a frightening concept.
Any other questions?
I'm just looking at the chats, but I think those are mostly comments rather than questions. I think.
So the thing I'm going to ask a question. The thing that you just said, like existing technology and works very well, that seems to cover a fair bit of everything that you've said this afternoon.
It does.
And just wondering when is this going to happen, and what's stopping it from happening?
Right. Look, that's actually a very interesting question. You might say, even in the agricultural application, where we're thinking of this importance of greening up agriculture. Let me just tell you a side story there. So one of our very, very keen kind of helpers and advisors in understanding the agricultural context is a wheat farmer from South Australia. She's probably a typical wheat farmer in the wheat belt of South Australia. She uses nearly 1,000 tons. That's an almost unimaginable amount of urea, right? So those white big sort of bags that get delivered, with sand or stones or whatever, if you've ever seen those around the place. So that's usually about a ton. So she uses 1,000 of those every year on the farm. It's not a particularly big farm, it's just an average farm. And she is desperate, and the price of that has gone up about 3 times in recent, literally in recent months, in about the last year to 18 months, because, like we said, your fertilizers today are made from natural gas. And the price of natural gas is going through the roof, as we all know, but it's hurting farmers. I mean, that difference in price is enough to make some crops just not viable, especially on a year of bad year in terms of rainfall. Doesn't matter how much fertilizer you put on, you still won't get a good yield. So this is quite critical for farmers to get independent control over their fertilizer supply and to be able to use it much more efficiently. So some of them are really, really excited about what's possible here. And as I say, go back to your question, Mick, the reason this hasn't really happened yet is that up until now, natural gas and other fossil fuels have been too damn cheap. So to make ammonia from green hydrogen was too expensive, but that economic dynamic is changing rapidly.
Sonia Layton, you've got a question. Would you like to ask that out loud?
Yes, I was just reading that, Sonia. That is a very pertinent question here. How can we ensure that the new technologies consider all steps of green chemistry at every stage of the life cycle? So
apologies for the waffle. I was trying to make it concise and I didn't really get there, but. Well,
no, but it is the right question. And I think, how can we ensure that? I think it is... It's partly education, so that starts with you guys and all the way through us at universities and so on, making sure that our technologists think in the right way about sustainability. It's probably also partly about regulation. There's a lot of talk at the moment about how we truly regulate and and properly sort of label, if you like, green products, so that green hydrogen and green ammonia, as they're purchased by farmers and even as energy sources, are genuinely green. You know, how do we verify that? So there's a lot of regulation that's required here. And just as an example of that, I think I'm right in saying that there's been a number of, I would call world-leading regulations created in Europe, mostly probably led by Germany, this is broadly now, on products, making sure that products are A, recyclable, and then B, basically fixable, so that, you know, things like washing machines can be pulled apart and properly fixed by an appropriate, you know, person. Whereas there was a trend going back 10 years ago where none of these things were built to be fixable. They were all built to be thrown out after a very short lifetime. And forcing that came to a matter of regulation. Right. And that, by the way, requires not just regulation on manufacturing industry in country, it requires regulation at the border, because there'll always be some country that's prepared to not do it this way, and we have to all stop buying those products. So that's an interestingly sort of topical topic.
Yeah, Doug, I wanted to ask you about that, about this idea of moving the onus away from the consumer, you know, across all sort of recycling. You know, instead of this big marketing push about people putting the right things in the right bins, what you've got to do is the people who make them are responsible for the end where it ends up in some way financially. Yes. And I guess that comes down to all of this, doesn't it?
Yes, it does. Absolutely true. So the manufacturer has to be driven, if you like, by one means or another into the right mode of thinking. And as I say, I think the German car industry is a good example. And it's probably true. My son works for Toyota. I'm sure he would say that it's true in Toyota as well. I just happened to have picked up on this in the German car industry. But equally, as I say, I think you said this too, Melissa, that it is partly about us as consumers making the right choices. But we need information, first of all, about what's the basis of our choice, right? So somehow or other we need better information about, you know, how has a product been made, how carbon intensive is it? There's lots of information we might choose before we buy that washing machine or before we buy that TV. And then ultimately that helps us understand how it might be recycled.
But it is very hard for the companies, isn't it? They can't make the leap until there's some sort of regulatory framework. Otherwise, they couldn't compete.
Yes. And the sort of information that we're starting to hint at that we might like as consumers, of course, we're all educated sufficiently that we can understand the information we're asking for, but the average person can't. So that requires regulation, I think.
Sorry, this is just an additional comment for picking up on the consumer stuff. I imagine what's going to happen though, if you know, washing machines and fridges are being built to last and be fixed, that the price point will go up, and that you know, people will need to really shift their expectations around what you pay for a product. And partly the reason why we've got this throwaway society is because companies are competing for consumers based on price. And I can see that would be a really hard push in our sort of capitalist, you know.
Absolutely. So yeah. Lisa, you know, I'm not actually sure how we make that transition. You know, do we look for a better level of education about all of this and hope that sort of there's enough people that head that way, or does it have to be fairly sort of strict regulation that basically forces some products out of the market? You know? Yeah. But you're right about the consequence. You know, this forces certain washing machines out of the market, or in other words, they're just not allowed to be imported.
But I think it also potentially locks out a certain socioeconomic group of people.
Yes.
Like from having a washing machine, if you change the price point, or maybe we
have to Lisa, there'd be more available that were
well, I was going to say
secondhand.
There might be a secondhand system or something like that, but would people be getting rid of them if you could fix them? Like, you know, like.
Oh yeah, there'd always be some people who wanted the new one.
Yeah. So I'm pleased to say that you know, in our centre, you might have seen that Centre of Excellence that was at the top of my slides, etc. We've got a number of policy and ethics researchers involved in our bigger group of academics, precisely for this reason, that there are things that, you know, we all tend to start discussing in our goal of being sustainable. And chemistry, you know, a lot of sustainability does start with chemistry, right? Because sustainability ultimately means, you know, recycling everything and losing track of nothing in terms of chemical elements. That's my extreme definition. But at the end of the day, these sorts of social questions and socioeconomic questions come up, and none of us, at least none of the people that I'm involved, are really well equipped to answer. You know, but I think it's probably a good topic to raise with your students. You know, they're the future. So the question is, what do they think? It would at least force them to start thinking about issues like this.
Definitely.
All right, everyone, we are out of time. I want to thank Doug very much for your presentation, and I particularly want to thank you for really taking the time to look over the study design and making it so relevant to what is in the current study design. And I think all of us know a little bit that this area of sustainability is going to be much more important in the next study design. And from what I've heard, that'll be released probably in about 2 weeks' time. So be really, I think it'll be really important for us to be continuing these kinds of conversations through next year and until everyone starts to teach that new material. So again, thanks very much, Doug. Thanks for making it so clear and so relevant. And I'd like all of you to join me in saying that thanks.
You're most welcome. As I say, it's always a pleasure for me to talk with you guys. And as I've mentioned throughout, and of course this is now recorded, so that it's easy to maybe access some of that information. There are a couple of things that could be useful resources for a student doing a project or something like that. All right.